Hey guys, so today's lesson is kind of two mini lessons rolled into one. They kind of have no relationship with each other, but they're two lessons that I thought I could teach them both in one day and kind of save us a little bit of time because they're both kind of, like I said, just kind of short. So the first half of the lesson is all about inverse functions, which we talk about in Algebra 2, and I think you talk about in Pre-Cal, and they kind of come back again. And so the first thing I want to do is just refresh your memories on what inverse functions are, how to find them, and kind of what their relationship are, all right? So I have right here example 1, if you have a function and it equals 6x plus 1, find the inverse of that function. And so the first thing I want to remind you is how do you find the inverse of a function? And I don't think this is something you're going to have to do on the AP test, but I'm just trying to get you in the frame of mind of what inverses are. So remember, to find an inverse, you switch x and y. You swap the roles of x and y, and then you solve the equation for y. You get y by itself. So I would subtract 1, divide by 6, so you get x minus 1 over 6, and that would be the inverse function. So you switch x and y, and then solve for y. And take that a step farther, the thing that's true about a function and its inverse is this. Like, if I would take a number in the original function, let's say I pick a number. Let's say I plug in 2, okay? Let's say I want to find f of 2. So I plug 2 into the original function, and I get 13. What that means is, in the inverse function, if I would plug in 13 for x, I should get 2 as my output. It basically switches your domain and range. It switches your input and output. And that would be the case here. So again, that's not anything you're going to have to do on the AP test, but just a reminder of functions and their inverses and what they do. What this lesson is about is all about what happens in example 3. It says complete the exploration on page 347, but I'm just going to go ahead and do that for you guys. I'm going to explain what's happening here, because this whole lesson is not necessarily what's true about a function and its inverse. It's more about what's true about the derivatives of two inverse functions. And it's a very, very easy thing that's true, but it gets tricky, and I'll show you in the last example down here at the bottom. So what the exploration does is this, and you could write all this out if you want to pause it for a second. But it gives you two functions, f and g, that are inverses of one another. So the problem gives you these two functions and says f and g are inverses. And then it wants you to find the derivative of each function. And so I did that. I got 3x squared, and I got 1 over 3x to the 2/3. I did the power rule, and I found the derivatives. Then the exploration says, okay, find f prime at each of these 3 points, 1, 1, 2, 8, 3, 27. Then it wants you to find g prime of 1, 1, 8, 2, and 27, 3. Basically at those same ordered pairs, but switching x and y. That's the whole setup of the exploration. They give you two inverses, they say find the derivatives, and then find the derivatives at these 3 places. Okay? So now I want you to see what happens when we do this. So if I find f prime at 1, 1, so if I find f prime of 1, just plug 1 in for f prime, and I get 3. And then if I come over here to g prime, and I want to find g prime of 1, so if I plug 1 in for g prime, I get 1/3. So f prime of 1 was 3. G prime of 1 is 1/3. So let's move on to 2, 8. So if I find f prime of 2, I would get 12. And then if I go over to g prime, and I find g prime at that same point, but notice what happens here. This is kind of the tricky part. And so the whole 1, 1 thing is kind of a bad example, because what's happening is we're plugging in the x coordinate from the point for f prime, and then we're plugging in the y coordinate into g prime. So while I did f prime of 2, I wouldn't do g prime of 2. I'm going to do g prime of 8. And let's see what happens. If I plug 8 in for x, I'll just tell you it's 1/12. And so look at the relationship between f prime of 2 and g prime of 8. They're reciprocals of one another, which is really the whole property, is that if you have two functions that are inverses and you look at each of their derivatives at the same point are going to be reciprocals of one another. And so if I do the very last one, if I do f prime of 3, if I plug 3 into f prime, I get 27, which is just a complete coincidence that we got the same y value here. That is irrelevant. But then if I come over here, we can make now the conclusion that g prime of 27 is going to be the reciprocal of what we got for f prime of 3. So it would be 1/27. So in conclusion, if you have two functions that are inverses, their derivatives at the same point are going to be reciprocals of one another. That's just kind of the new concept. You might get one question about this on the AP test, and that's a maybe. It's not something that shows up a ton, but I have this example down here at the bottom, and I think this was from 2008 maybe, but this was the most missed problem on the AP test in 2008, the most missed multiple choice problem. And so I want you to pause this, and I want you to see how it can be tricky. I want you to pause this and see if you can get this answer right. And then I'll walk through it and kind of show you how it can be a little tricky. Okay, so first of all, the answer is A, -1/2. So if you tried it on your own, and hopefully you did, because if you didn't and you're just taking my word for it, you're not going to find out how these can be tricky. But the answer is A, -1/2. And so here's kind of how I go about these problems. It asks for g prime of 3, and the first thing I notice is it tells me g and f are inverses, so my brain's going to think reciprocal. I got to think about reciprocals, okay? But here's what I do. If they tell me f of 3 is 15, right, then I'm at the ordered pair 3, 15. And then I'm like, okay, they tell me f prime of 3 is -8. The biggest misconception is students will say g prime of 3 is -1/8, the reciprocal of this. That's kind of the tricky part of the problem. B is the most common wrong answer, okay? But here's the conclusion. If f prime of 3 is -8, I can conclude that g prime of 15 is -1/8. So it's not the reciprocal at the same x value. The slopes are reciprocals at, you plug in 3 for f prime, you would plug in 15 for g prime. Those are what are reciprocals. And then the next thing I know is, okay, f of 6 is 3, so 6, 3. And if I know f prime of 6 is -2, then I can conclude g prime of 3, so this y value, is the reciprocal of -2. So -1/2, and that's where A comes from. So while it's a very, succinct, short property, and you might be asked one question on the AP test, oftentimes it could be a tricky question. So just be careful. All right, so that's a new concept. Now let's dive in to the next thing, kind of its own little mini lesson also. So this here, I want to take you back again to Algebra 2 and to Pre-Cal, and you guys learned an interest formula where interest compounds continuously. And that formula was A equals PE to the RT, PERT. We're not going to use this formula, okay? But that leads into general growth and decay, which hopefully you learned this formula. I know you did in Algebra 2, but I imagine you did in Pre-Cal as well. Is this thing right here. And sometimes they use different letters. I think sometimes they'll use an N where the C is. I put C there for a reason. You'll see as we go through the example here, okay? But I want to talk about where this formula comes from. This general, when things grow or decay continuously, this is the formula we use, and I want to show where this comes from. So let's take a look at where this formula comes from. And yeah, this is heading somewhere. It's leading into kind of the skill that we need to learn. So remember what it means for things to be directly proportional. For things to be directly proportional, that means that if y is directly proportional to x, then y equals k some k value, times x. Remember, if it said inversely proportional, that would be y equals k divided by x, but we're only going to focus on things being directly proportional, okay? That means as x goes up, y goes up. That's what's happening here. And as x goes down, y goes down. So the problem says, if the rate of change of y with respect to time, so I want to focus on that right here. The rate of change of y with respect to time. Think about how we write that notation. The rate of change of y with respect to time is dy dt. If that rate of change is directly proportional to y itself, so the way we'd write that is equals k times y. And a way to think about what this means and what this is saying, okay, it says the rate of change of y, so how fast y is growing, is directly proportional to y itself. What that means, I like to associate this with like a bunny rabbit population, right? You have some bunnies, and then they do stuff, and then there's more bunnies, right? And then as there's more bunnies, then they do stuff, and then there's even more bunnies, right? And the bunny rabbit population explodes. And so basically, as there are more bunnies, the rate of change of how many bunnies there are exploding. Like the population grows quicker if there are more bunnies. That's what this relationship is saying. The rate of change of y, how fast y grows, is directly proportional to y itself, how many bunnies there are. Now that doesn't matter a ton. What matters is this next question. And this is going to lead into the skill. We are going to be solving a lot of differential equations in this class. And when we solve differential equations, I want to go down to this example right here, example 2. When we solve a differential equation, this is the whole separate and integrate scenario. Separate the variables and then integrate both sides. The whole thing where I've said if you don't separate, then you get 0 out of 5 on your AP test. So that's what we're going to do here. When it says solve the differential equation, I want to go backwards. I know dy dt, but I want to go backwards and find y, okay? So when we do that, this is where we separate the variables. Now, this is where students get a little tricked because we have a dt. Normally, it's pretty easy to see. You have y's and x's, and it's easy to see the separation. These types of problems, it's tougher for students because there's a dt right here, but there's no t anywhere else. Well, we need to get the y's on one side, and we need to move the dt over to the other side. So I'm going to first divide both sides by y. So I'm going to have 1 over y dy. And I'm going to multiply both sides by dt. So I have k times dt. So all I did was separate the variables, okay? Now think about when we separate, now we integrate. So I'm going to integrate both sides. And when we integrate 1 over y with respect to y, this is the natural log that we got last time. So the natural log of the absolute value of y equals. And when you integrate k, which is some constant, I don't know what it is, but when you integrate k with respect to t, you get kt, and then we have to put plus c. And the reason I'm showing this is because if you come across an AP problem, a free response problem, where you have to solve a differential equation, odds are it's going to be one like this, where you're dealing with natural logs and things like that. They're able to assess a whole lot of knowledge in these types of problems. But I'm not done. I'm trying to figure out what y equals. So I know those of you in physics, I think he always says like e both sides, e it. Well, I'm going to take this log form and turn it into exponent form. If you remember, right here you have like a base of e, and if you change something from log form to exponent form, it would be e to this power equals y, right? So it'd be e to the kt plus c power equals y. We're almost done. The whole thing I've been trying to do to refresh your memories, because it seems like I'm not going anywhere, I was trying to show you guys where this formula comes from, okay? And this formula comes from when you have a rate of change of something directly proportional to that thing itself. Well, look at what we can do in our final step. This is kind of the manipulation students get a little confused with. So if I have y equals e to the kt plus c power, okay? Well, think about exponent rules. E to the kt plus c. Think about how we can rewrite this. This is the same as e to the kt times e to the c. And I want you to kind of wrap your brains around this here for a second. Think about when you multiply two things with the same base, you would keep the base and you would add the exponents, right? Like if I went from the right side to the left side using exponent rules, that makes sense. Well, we can do the same thing going from left to right. And all that happens here, well, if c is an arbitrary constant, if we take e to some arbitrary constant, then we just get a different arbitrary constant, some other c value. And so this becomes c times e to the kt. And that's where that formula comes from. Now, I don't think you're ever going to have to be doing this exact problem on the AP test. I'm going to skip example 1 here. But I want to show you guys our last example and when this skill is going to be used, okay? So this one says, this is what you're most likely to have to do on an AP test. It says solve the differential equation. And when they say that, that means they're giving you a derivative and they want you to go backwards and find y. And you can't just put the integral sign right here. You have to separate and then integrate. Separate your variables. So to do that, I'm going to divide both sides by y minus 1. So I would have 1 over y minus 1 dy. And then I'm going to multiply both sides by dx. So x squared dx. And typically you get a point just for separating like this. Now I'm going to integrate both sides. When you integrate 1 over y minus 1, you could do u substitution. You could have u be y minus 1 and go through all that, but you're just going to get the natural log of the absolute value of y minus 1 equals 1/3 x cubed plus c. I would encourage you to pause the video and see if you can solve this, if you can keep going. And then I'll show you guys 2 different ways to do this problem. So pause it, try it, come back. Okay, so option 1 is, I know I've advised you guys right after you integrate to plug in your initial condition to find c, and you can on this, and I'll show that, but I'm going to do it this way. When I'm dealing with this, I'm going to do e to the 1/3 x cubed plus c equals y minus 1. So all I'm doing is changing this from log form to exponent form. And the reason the absolute value can go away is because whatever you raise e to, like e to anything, is always going to be positive. So the absolute value at this point in time can go away. You don't need it anymore. And then I'm going to do what I did up here on this example, where that e to the kt plus c right here, how this just made that c go out in front, I'm going to do that here. So I'm going to rewrite this as c e to the 1/3 x cubed equals y minus 1. Now I'm going to solve this for y. So I have y equals ce to the 1/3 x cubed plus 1. I'm adding 1 to the other side. So I get y by itself, and now I'm going to plug in the initial condition. I still need to find c. So I'm going to plug in 3 for y and 0 for x. So think about what happens when I plug 0 in for x. I would get, well, e to the 0 is 1, so I get c plus 1. So c is 2. Which means my final answer would be y equals 2e to the 1/3 x cubed plus 1. This is typically going to be a 5-point problem on a free response. You get a point for separating, you get a point for each of your integrals, you get a point for finding the right c value, and then you get a point for having the right equation. That's usually how these problems go. They're kind of like jackpot problems. So I want to show this way. If you plugged in your initial condition here, I want to show this. So if you plugged in 0 and 3 at this point in time to find c, you can, and you can still get the right answer, and I want to show that. So if you do that, you would have the natural log of 2 equals c. Because you would plug in 3 for y and 0 for x. And then if I rewrite this, I would have the natural log of absolute value of y minus 1 equals 1/3 x cubed plus ln of 2. So if you did it this way, here's what you would have. Now I'm going to turn this into exponent form. So e to the 1/3 x cubed plus natural log of 2 equals y minus 1. I'm just turning that into exponent form. And if you do it from here, well, think about what happens here. I could rewrite this as e to the 1/3 x cubed times e to the ln of 2. And using our log rules, e to the natural log of 2 is just 2. So this would become 2 e to the 1/3 x cubed, and then add 1 over. So you get to the same answer. I think for these problems with logs, it's easier to solve for y first, but it's completely up to you how you want to do it. All right, so like I said, just two kind of mini lessons. The relationship between derivatives of inverse functions. And then this one, this whole beginning problem, if this didn't make sense, really I just wanted to show you an application of solving a differential equation this way. But mainly this last example is what you're going to be up against right here. Just separating, integrating, dealing with natural log, and finding a c value in this way. All right? Let me know if you have any questions.